If you want. And it's also easy. Once I finish this one here, I'll write the comments. Oh, because of, yeah, you're definitely. Hopefully, it's gonna get to this.
Hey, good afternoon, guys. So I want just to comment about first homework that um, we we worked on the translation, and I asked to print the number of words from your training dictionary, and uh, for this first sentence it was just four. It means that all the other words were matched by the closeness of word embeddings. And it was interesting to me to see the name, that the name Sophia was matched to another name, Casper, but still name. So, um, and we had only two words matched exactly in this phrase. Okay, so let's finish our week two. Week two about the different ways to create one vector from multiple vectors. So last time I was talking about attention, but it wasn't the attentive pooling. It was, for some reason I started to talk about self-attention, and when that's why when I saw my code, it looked different to me, but the code actually was correct. The code was for attentive pooling. So now let's um, just revise that, and hopefully we'll go to the topic of this week, language models. So let's create let's import first libraries, import torch. Um, then from torch import nn, and we don't need other things. So I will create just a batch of tokens with some numbers and padding. And 1, 2, 3, 4, 5, and one more. So I just, as you remember, numbers represented the words, the tokens, and one stands for padding. So if we want to apply, then we convert this into embeddings. So I will create also embedding layer. Of shape, let's say 10, because my maximal number is 7, to, let's say 5. And then we can map this embedding of batch, and we will get okay, 5. Okay, 5 is the same as the number of my elements. Let's do maybe 6. So we will get the for each element in our batch, we will have the vector of size 6, and we will have 5 vectors of size 6. So, and the length is 5, so we change the dimensions. So we will use transpose 2 and 1 to get the time dimension is the last dimension. So we change.
What is the last dimension?
Oh, so as you remember, this represents the sentence.
Mhm.
So this is kind of time. So the first token, the first word, second, and so on.
Okay.
So 1, 2, 3, 4, 5, and when I apply embedding, these 5 will be actually the second dimension, but I want to make this as the last dimension. So this is kind of time dimension, and this is the size of embeddings. So let's talk about this attentive stability. So now we have, instead of numbers, we have vectors, embeddings, 5 embeddings for the first, then for the second. The first dimension is batch. The second dimension is the size of embedding hidden, and this is actually the length of our phrase. So this is what represents this tensor. And we want to get one vector. So for attentive pooling, we will apply just a linear layer that will shrink these dimensions into 1. And we will get some numbers here, and we will sum up these vectors with these numbers. So let's create a linear layer, fully connected and linear, and it will go from the hidden size to 1. If I apply this fully connected, let's let's call this embedding transpose somehow, like embedding input, in. Embedding input and embedding input um, um, and I will apply my linear fully connected to embedding in. And if you look at the shape, what? Let's see. Oh, because it should be, let's see. Oh, okay. Linear layer, if you look at the description, it's actually applied along the last dimension. So linear layer is applied the dimension of the input is the last dimension. So I should transpose back. So I should transpose back. And then when I apply linear layer, I will get batch size, but the dimension of my vector 1. And this is time. And now I want to make the time the last dimension. So after fully connected layer, I again transpose it. And then we will get the correct dimension with batch free. One, one will stand for this constants alpha, and 5 is the time dimension. And then we can multiply this fully connected, let's call it H, for example. Then I will multiply H by my input by H by my M in, embedding in. So embedding in has this shape. My H has shape 361. So when I multiply, it will actually will perform multiplication of each vector of here of size 5 by the vectors of size 1. And after that, I will just add them together. Sum. So I believe it's torch. I can just use postfix sum along the last dimension. And the result only integer tensor and singleness can, let's see. What is the shape of this product? Hmm.
Each is set equal to the shape, not the result of in the cell above.
And what?
You adopt shape after going through the fully connected layer.
Oh, I'm sorry. I didn't.
I thought
Yeah, I have an integer here. Yeah, I should remove shape, and then it should work. So sum along the last dimension. Thank you, Matt. Yeah, and this is the expected result. Now we have a batch of 3 and 3 vectors of shape 6. So now instead of 5 vectors of shape 6, we have just 1 vector of shape 6 for each element in our batch. So this is called attentive pooling. Last time, for some reason, I was talking about self-attention and talked about multiplication, the product, but attentive pooling is much easier. Okay, the last thing is recurrent neural networks, how to get one vector from the sequence of vectors. Let's talk about that, and we will go to the new topic. So let's create a recurrent neural network, and I will use LSTM. So in LSTM, the input shape will be, in my case, 6. The output shape will be, let's make maybe 10. And batch first, because if you look at the description of LSTM, it by default the and again the by default the batch size is the second. If you use batch first, then the batch size will be the first. So I used to see batch as the first coordinate, and then again the dimension is the last component, and time is the upper last. So we will need to again transpose our batch. So I can apply RNN to my batch, but I will need to transpose first and 2. So dimension of range. So batch. Oh, sorry, it's shouldn't batch. It should be embedding in. In. So LSTM returns actually three parameters. One is the output, and then state and hidden. I believe CH or HC. Let's double check. HC. So and oops, it's wrong. And H and C. So just a quick reminder how LSTM works. It takes as input the sequence of vectors and returns the sequence of vectors, but of different size. So this out actually will contain the returned sequence of vectors, but of shape 10 in my case. So we will have the same number of vectors, but of different shape. And this is what will be stored in out. H will be this one, the last vector, H. And C, we don't care about states of our cells. So, yes, and as you remember, in recurrent neural networks, we assume that all the information about this input phrase contains in the last output hidden vector. So just take the last vector and it will be one vector from this input sequence. So just you can just use like dash you could use just dash h dash equals, and this will be your actually representation of the entire phrase. Let's see. We have extra dimension 1. You can do squeeze. And oops, before shape. And then you will get the desired dimension, batch size, and just one vector, in this case of size 10. You can use bidirectional also parameter bidirectional equals true. When you use bidirectional equals true, it returns actually two like two layers, and the output shape will be twice. This is H. So for H, you will have two channels. One corresponds to the forward path, and the second channel corresponds to the backward path, because bidirectional, it's kind of we apply LSTM twice. And you can just stack along this dimension and create one vector. Okay, I will show how you can do that. You can use output, for example, 0 and output 1, and stack them together. So what is that? Torch dot let's see if vstack works. If not, concatenate maybe I should use list. Yeah, wait a second. But why it's 10? Oh, because I stacked along this dimension, but I want to stack along. Oh, what is that? Second dimension or the last one? Let's see. Okay, maybe concatenate. Concat? Oh, the same. Yeah, okay, so this works. So LSTM bidirectional returns two vectors, like last vectors. And you can just concatenate them, and then it will have twice longer shape. Or as you remember, we had a lot of paddings. And when our neural network goes along our sentence, and then it will see, for example, padding of size 100, maybe it will forget the previous information. So it's better in this case, in case of padding, it's better to take not the last embedding, not the last vector h, but the embedding with the first padding token. So to do that, so output shape, I will print shape output in case of bidirectional out dot shape. Output actually it concatenates. It doesn't create two channels. It just concatenates forward and backward paths. So that's why dimension is 20. And as you remember, with the padding was only from the right. So for actually, I don't remember. The first is the first or the second is the forward. Let's see. Output. Of the forward and reverse. So I think the first part of the vector will be from the forward part and the second from reverse. At least I would understand this. So you can look at the, you can create a mask of your batch. Mask batch not equal, and the padding was 1. So if you look at this mask, it will return true, false. So false stands for the padding token. And if you sum along columns, you will actually get the index of the last not padding token. So if you sum along the last dimension, you actually will get the indices. So where was our batch? I will print batch. Actually, you will get the indices, but shifted by 1. Yeah, because the indexing begins from 0, but with some. So if I subtract 1, I will get correct. Oh, not here. Sorry. Here, sum minus 1. I will get actually the correct index of the last not padding token. So index 1, index 2, and index 4. And it's a good idea, instead of taking the last vector after a recurrent neural network, to take the vectors corresponding to the last not actually padding token. Because padding doesn't contain information about our sentence. And we want to have information about our sentence. So to get these vectors from our output, because output stores all the vectors instead of just the last one. We can do the following. So we can, so I will erase these drawings. Let's call this index. So okay, maybe AI assistant will help me. So I want to first extend torch. Okay, AI assistant helps me. So there is a function gather that will take the elements from your tensor by indices. And I didn't remember the name of this function, but so gather. So what we're doing here, so we have our output from LSTM, and for now I will just use, for example, the first part, so out and just the first 10. So they correspond to the forward path. So what is that one? I don't know. And here we will do index unsqueeze. So instead of index unsqueeze, you can do just like that. None. So we add 2 dimensions because our output has 3 dimensions. We create 3 dimensions for this indices. Then expand will multiply these numbers along desired dimension. In our case, it will multiply these numbers along we should multiply the numbers along the size of our vector. So what is the shape of output? 20 is the last dimension, then that's along the last dimension. But output shape in our case is just 10. So expand will just repeat these numbers 10 times. Because does it make sense? Because we want to have for element like for batch equals 1, we have the vector of size 10, and we create the tensor that has index 1 repeated 10 times. For batch 2, it creates a vector where index number 2 is repeated twice. So after applying gather, it will actually take the vector with index 2 from our output for the first batch, for the second, the vector with index 2, and so on. So let's see the result. The result should be, oh my gosh. It does like something. Let's see. Let's try to apply separately expand to my index. Yeah, it looks good.
One before index none.
Oh, and what does it mean, one? But it's working. Yeah. Let's see. Okay, let's just ask ChatGPT what does it mean, one? What? One. Mhm. Oh, its dimension. Okay. Gathering happens along the second dimension. Okay. So, yeah, this is how you can actually extract not the last hidden vector, but the last before pairing. And hopefully it will contain more information about our sentence than after looking for patterns. Okay, great. Now let's go to our topic of this week, which is language modeling. Finally, I also prepared the code for today, but I think we won't have time. So, and again, we will talk about count-based and neural network models. So what is the model? It's something that just looks like the real thing. Like this is the model of train. And the same is with our language models. It's not the real thing, but it looks very similar to, very familiar to our language. So I will skip this introduction about language. So there are different ways to recognize speech, but let's skip it and let's go to the general idea. So you remember how to calculate the probability? It's just to count these balls and we'll find the probability. So the same with words. We can look at this phrase and search in our data set, in our corpus. And if we don't find this phrase, we will return probability 0. If we find this phrase, we will return the count over the total number of words. And you can see the problem with this approach, that large phrases unlikely will be in our data set because there are millions of ways to say something with different phrases. So the solution is to use small phrases, which is called n-grams, just n consequent words. If we use, let's see, for example, we can calculate the probability of one word, of word I, and it's straightforward. Oh, I think it's the visualization is on NLP course for you. Mm, oh, yeah, there is visualization. So, for example, the probability of one word is most likely we will be able to calculate because this word will be in our data set. Then we want to calculate the probability of the second word based on that we saw the previous word. And like I saw, and we will calculate the probability to see this word pair, I saw. Then we will look at the probability of the phrase I saw a, 3 words. But if we will continue this process, at some point we will maybe run into long phrase, and the probability will be 0, maybe somewhere in the end. And the entire probability of the phrase will be 0 because we multiplied the probabilities. So we can use the idea of n-grams and look only at not all the previous words, but at maybe 2 previous words. Then it will be 3 grams. Okay, so this is how we can generate, for example, the probability of the we have the probabilities of the next words, and then we just sample a randomly sample from this distribution a next word, the next token. I mean, we can take always the token with highest probability, but then we won't have this like naturalness in our language. So ChatGPT will generate always the same answer on the same question, but it generates different because it samples from most probable words. But it doesn't solve the problem with 0 probability for like long phrases. But this is the main idea, how language models work. We want to we want to get the next token based on the previous phrase, and we have some probabilities, some distribution of the words for this previous phrase, and then we choose the new word from this distribution. So yes, instead of looking at all previous words like first and second, all the previous phrase, we will truncate again because the numerator can be 0 because if we don't see this phrase in our corpus. We can truncate and, for example, at time t, we can look only at 2 previous words. That's time t minus 1 and t minus 2. And this model is called 3-gram model because we will calculate only triples of the words. If you look only at the previous word, it's called 2-gram or b-gram, and then we can just look at one word, then it's a bag of words. And then the generation will go like this. So the first word, then it will calculate the probability of the second word, so based on the previous word. Then it will calculate the probability of A based on I saw. But for the cat, it won't look at I, it will look only at saw F. So this is the idea of tree graphs. And of course, the advantage of this model is that we won't run into a problem with zero probabilities, but the problem is that we actually don't look at the previous context. We look just 2 steps behind. So let's go back to slides. So yeah, and still we may have this problem with zero numerator, and there was idea which is called stupid backoff. If we don't have triples of words, look at the tuples of words. If we don't see tuples of words, look just at the individual words and substitute this problem. There is a not stupid backoff when we take the weighted sum of this like bigrams, 3 grams, 1 unigrams. But again, it's all about counting. And in practice, typically used Laplace smoothing when we just, to avoid zero probability, just add a small number. If a number is 1, then it's called advanced smoothing. If it's arbitrary number, it's called Laplace smoothing. And there is more clever smoothing, which is called Neisser-Ney, and it's used in mobile devices when we don't have enough memory for neural networks. So it works pretty well. And we have 4 minutes left. Let's see, maybe we can go through notebook that I prepared. So actually, I wanted to code with you, but I will open my ready notebook just to show how this model works. And upload. Okay, so this is how we can write the scientific paper. So the data set is from archive, and now we will write the research paper based on this data. So let's upload the data. So these are the articles. Then I add concatenate title and summary. So it's all just data preparation. Then we tokenize. So actually what I was thinking to code with you, but for now I will just run. And then we count n-grams. So counter will count n-grams. And now then we will calculate these probabilities by this formula. And finally, let's test it. So this is actually, I think, straightforward to code. So in the interest of time, we can just run this populated notebook. So I will create this model that counts n-grams. And now, which will be the first word of your article? Huh? I had GNN, but you what will be your article about?
Did you do P equals NP,
What?
like the famous problem?
P
I don't think.
equals. The counter is 0. What if we just use P? Oh, actually, it's lowercase. I use lowercase. Let's try P equals and P with lowercase. It's still empty. Let's just try NP. And it says that the next most likely token is dash or animacy. Okay, NP dash. What will be next? Then it provides the choice, and the most probable is NP hard. Okay, very good. We started to write our article. NP hard. Okay, let's try next word. The next word will be point. Okay, period. And after that, in. Okay, in. But if we continue this process, I'm choosing. Yeah, I'm doing the grid search. So after in, there are a lot of choices because our model saw a lot of pairs in something. Then it says in both. So if you will continue this process, you will see that there is no sense because it looks only on 2 previous words. And it's fine on the local intro, like NP hard. Yes, it sounds good, but then it doesn't make sense. Okay, so let's stop here for today. And next time we will go to neural network language models.